It's silent, odorless, deadly. In the bustling LA neighborhood of Watts, residents face an invisible threat: lead contamination. Many aging water pipes release microscopic particles of rust and lead, clouding the water and endangering health, especially for children. According to the EPA, even trace amounts of lead can cause permanent developmental effects. Luckily, there are many solutions. This is our hybrid turbidity and lead detection device. A small sensor indicates when it's found lead and other contaminants in water. Each part plays a vital role. The turbidity sensor measures the cloudiness of water, an indicator of suspended particles that often appear in lead-contaminated areas. When cloudiness surpasses a safe threshold, it sends a signal to the lead module, which lights up bright blue. The two compact battery cells power the circuit, all encased in the 3D printed chamber for protection and integration into water pipes. Turbidity refers to how much light is scattered by particles in water. The cleaner the water, the less scattering occurs. But when corrosion or lead particles are present, they cause the light beam to scatter intensely, a principle measured by optical sensors in nephelometric turbidity units, or NTUSs. According to a 2023 U.S. Geological Survey report, increased turbidity in old plumbing often correlates with higher concentration of heavy metals.
In our detector, this relationship forms the first warning system. The turbidity sensor reads the clarity of the flow, translating those readings into an electrical signal, our first indicator of possible contamination.
Electrochemical lead sensing relies on detecting changes in voltage when lead ions are present in water. In advanced systems, this happens through a process called anodic stripping voltammetry, where ions are drawn to an electrode, then released to measure current peaks. Our prototype demonstrates this concept visually. When contaminated water interacts with the turbidity sensor's conductive probes, it mimics that electrochemical response. The LED turning blue represents a simplified version of what real sensors detect: changes in electrical conductivity and flow clarity.
By combining optical turbidity detection with electrochemical simulation, our device bridges two sensing methods into one simple visual alert system.
For the sensor to work properly, water must pass smoothly through the chamber, a concept known as laminar flow. In laminar flow, liquid moves in parallel layers with minimal mixing, ensuring consistent readings at the sensor's surface. We designed the 3D printed chamber to minimize obstruction and turbulence, maintaining steady pressure and accurate detection.
If water flowed chaotically, what's called turbulent flow, air bubbles or uneven velocity could distort the sensor's readings. By placing the turbidity sensor at a strategic midpoint in the flow, the detector captures reliable, repeatable data every time water passes through.
When clean water passes through, the LED remains off, indicating safe clarity levels. Now we add a little bit of simulated contamination. We have rust particles in black ink to simulate lead corrosion.
Immediately, the sensor detects increased turbidity. The system triggers a voltage shift, and the LEDs flash bright blue, a visual warning that contamination is present.
This output confirms the detector's core function, translating physical changes in water quality into a simple, visible signal.
The Watts community, like many others across the country, continues to face aging water systems that risk lead exposure. Our detector offers a small but vital step towards local awareness, empowering residents to notice contamination early before it becomes a crisis. Whether used in schools, apartments, or public centers, this model shows how engineering, chemistry, and physics combine to protect one of our most essential resources: clean water.